The Collatz conjecture is typically presented as a sequence of forward steps, but treating the math this way turns analysis into an infinite, chaotic branching problem, where the numbers climb and plummet unpredictably. To analyze this mathematically, we start here. This equation is the accelerated odd Syracuse map. It calculates the next odd integer in the sequence by multiplying an odd number n by 3, adding 1, and dividing out all the factors of 2. The denominator dictates how many halvings are absorbed in a single step. Because that number of halvings varies wildly depending on the input, forward iteration creates an algebraic wall. It blocks any clear view of the sequence's long-term properties. To apply higher-order operator theory and solve these properties, we have to establish exact arithmetic relations instead of just running simulations. This requires a strict new discipline: arithmetic first, representation second, compression third. We have to ground every finding in the genuine map before moving to abstract algebraic systems. This means running the map in reverse. By shifting from forward iteration to calculating the inverse branches, we track where the sequence came from rather than guessing where it will go. Tracking these inverse branches allows us to pursue the ultimate objective of this framework: compressing multiple complex sequence steps into a single mathematical evaluation. This compression converts an infinite step-by-step computational simulation into a finite deterministic check. By abandoning forward iteration and prioritizing an arithmetic-first inverse model, we can transform chaotic Collatz sequences into predictable, manipulable algebraic structures. We begin by isolating the accelerated forward map. The exponent in the denominator dictates the number of halvings. We isolate the specific component and redefine it as the variable k. To find the preceding odd integer, we algebraically rearrange the equation, solving directly for the initial input variable n. This process yields the single-step inverse branch. By plugging in an odd integer y and a chosen number of halvings k, we calculate exactly which odd number n leads to it. This formula provides exact arithmetic stability. It maps perfectly backward every single time, bypassing the chaotic variance of forward mapping. To ensure this architecture is sound, the forward map stability was tested across 1,000 odd integers. Then the inverse map underwent direct empirical verification. The inverse formula was tested against 13 specific targets, including 1, 5, 13, and 101. It recovered the exact original input every single time. With a structurally verified, exact single-step inverse now established, we possess the reliable foundation required to start chaining multiple operational steps together. A single step is useful, but a sequence of specific exponent iterations, which we define mathematically as a word, allows us to map extensive Collatz chains. Nesting the inverse function for every step m builds a continuous multi-step sequence. Instead of calculating sequentially, this chain collapses into a single affine formula. K represents the sum of all exponents across the word, and C is a recursive constant derived directly from those exponents. Evaluating this single calculation immediately yields the result of m discrete Syracuse steps simultaneously. Theoretical compression requires direct empirical testing to prove the arithmetic holds at scale. When evaluating the specific 5-symbol word of 5, 3, 2, 4, and 1, the compressed recursive formula calculated a constant of 22,705. This exact constant was then checked against the long-form sequential calculation. The exactitude was confirmed across 7 distinct test words, producing 0 mismatches. This verifies the compression third discipline, transforming a disparate sequence of operations into a predictable algebraic evaluation, relying only on variables k and c. To apply this math to the Collatz conjecture, we must prove admissibility, the strict requirement that inverse paths remain entirely within positive odd integers. Normally, proving admissibility requires confirming every single intermediate step evaluates to an integer. Our architecture moves past this step-by-step verification, using a single mathematical identity. This is the single congruence theorem, providing the terminal condition for the entire path. The math functions through downward induction. A verifiable algebraic identity links the constant of a given step to the constant of the step preceding it. Because of this linkage, satisfying this one top-level congruence mathematically guarantees that all preceding intermediate values are perfect integers. Once we know the outputs are integers, we still must satisfy the exact valuation condition, ensuring these integers are strictly odd. This is solved by the self-propagation lemma. The arithmetic dictates that any valid integer generated by this inverse map is strictly forced to be odd. To verify the theorem across a wide computational range, it was tested against word lengths 1 through 4 across an alphabet of 1 to 4, resulting in 22,620 combinations, all with 0 mismatches. The terminal condition solves for admissibility in a single step, bypassing the cumulative resource drain of intermediate checks. With a fully verified compressible architecture in place, we can apply it to the ultimate goal, systematically hunting for non-trivial collat cycles. We start by bringing back the compressed affine formula. Finding a cycle means finding a fixed point, where the sequence loops back to equal the input. We set both to x. Rearranging this relationship yields the absolute constraint for cycle existence, the cycle equation. This reduces an infinite simulation to a finite mathematical search for integer divisors of the constant c. For any cycle to exist, the term 2 to the k minus 3 to the m must divide cleanly into c. To prove this fixed point model works, we test it against the only known loop in the Collatz conjecture, the trivial cycle. The trivial 1-2-1 loop is represented by the simple sequence word containing just the number 2. Substituting the variables for this trivial cycle into our equation gives us 2 squared minus 3 to the first power times x equal 1. The arithmetic resolves perfectly to the correct fixed point of x equals 1. Testing other repetitive words yields only non-integral or negative solutions. This proves the equation does not generate false positives. We also confirmed the system's algebraic uniqueness through a faithfulness test. Out of 3,905 words evaluated, there were 0 mapping collisions. Distinct words produce distinct maps. The natural continuations for this research involve proving that uniqueness formally, refining admissibility for full words, and developing systemic divisibility constraints to narrow the search space further. By utilizing an arithmetic-first discipline, this framework has successfully reduced the infinite Collatz simulation down to a finite, exact fixed point equation, paving the way for advanced operator theory.